Test. Okay, so now we have audio. So this is activity 4, effective inductance, reactance in an AC circuit. Now, when I launched this one time, it did not show, it seemed to me it didn't show all of the steps. So it is working now, but if you can't find all of these steps in activity 4, me so I can contact Amatrol, but I could be wrong on that. But anyway, let's proceed, because you're going to need some values. You're going to need to know the henries of the solenoid coil and the henries of the transformer in order to finish your skill 2. Now, they have been placed in the course layout, but I'm going to walk you through this. It's not so clear in the online part, but if you do open up the skill PDF in the hardware portion, then it becomes a little bit more clear as to what they are asking for. So anyway, I have both. Here's our activity 4 for the hardware, and it's all listed out here, and it gives us some formulas. So I have the simulator open, and I'm going to walk you through this. First of all, our coil is 90 ohms. I'm going to remove my leads. I have a DC power supply. And I've selected amps for DC. Hook this in series. Set for 24 volts. And I see that I am pulling 0.27 amps on this coil. So you need to remember those values, because now we're going to do the same thing with the AC power supply. And the inductance reactance, the collapsing magnetic field of the AC, is going to make our current go down, because it's going to it's going to act like more ohms than 90 ohms when we pass AC current through this. So basically your ohms are going to go up, and we have to calculate those values. And those values depend upon the frequency of the AC voltage a little bit. Here is our AC power supply. We are going to adjust to 10 amps. And this is what it did to me earlier. So that simulator is not working. Give me just a second. Let's refresh this very quickly. And if you wanted access to that PDF I'm going to be referring to, you can click on the hardware and it should open up. But we're going to go to the simulator. Hopefully this will work a little bit better this time, because the value should have been 20 milliamps that we read. So we're going to walk through here, and it says connect it like this. We're going to add our AC power supply. And that looks a little bit better. So now we see that we are pulling 0.02 milliamps instead of our 0.266 we calculated, because Ohm's law would have worked out with 90 ohms to be 2.66. And here we have a different value. So how do we find our henries? Well, we're going to have to backtrack, because you're going to have to know the AC voltage here before you can calculate anything else. So we'll go to the next step. And here we see that it is showing 0.2 on the 10 amp scale. This is much less than the 267 milliamps, because our inductive reactance has actually increased our ohms, because it's measured in ohms. So let's go and calculate the inductive reactance. Here is Ohm's law. So we know our voltage is 24 volts AC. And we want to actually calculate the ohms that are taking, basically inductive reactance is kind of like the ohms, but we're taking into account the collapsing magnetic field. We still measure it in ohms, but we're going to have to backtrack. We're still using Ohm's law, but instead of considering this our standard ohms, we're using XL, which is inductive reactance ohms. So let's go to our camera. And we have 24 volts AC divided by 0.02 amps to get our XL. Which gives us an XL of 1200 ohms. And so now that we have our 1200 ohms, we can calculate the inductance. Here's the formula for inductance. So formula for inductance, we'll close this out. And I've put these in your formula sheet. Now you see that formula here, but we've calculated it, and if we had our henries, we could calculate XL, but we didn't. So how do we get our henries? Because that's what they're going to ask for. So we can backtrack that, and we can rearrange this formula into L equals XL divided by 2 pi times the frequency. So we have L equals XL, and we determined earlier that our XL was 1200 ohms. So let's plug those numbers in. First of all, when we calculate pi, we're going to substitute this as in 1200 ohms of XL divided by 2 times 3.1416 times the frequency. Now your skill is going to say do this with 50 hertz because that's your European frequency. So basically what they're saying is stuff is going to pull a different amount of current in Europe than it does in America, because if it's on AC voltage, the inductive reactance is going to change that. So here we have this and our frequency. Let's go with America, which is 60 hertz, because our power supply in the simulator is going to be rated for 60 hertz. And so if we do the math on that, we'll see that we're going to do the bottom first. So we'll do 2 times 3.1416. Take the result, 6.2. We're going to multiply that by 60 hertz. And so that's going to come down here and give me 1200 divided by 376.992. So we're going to take 1200 divided by 376.992, which will give us 3.18 henries for that solenoid at 60 hertz in America. And you will need those numbers to help calculate that. So we've gotten that. So skill 2 is going to require those henries and XL. You need to keep up with those. And I've listed them. So let's go ahead and look at the second part of this, and let's look at a transformer. Add a transformer. We're going to add a digital multimeter. First of all, we could obtain the ohms if we wanted to. That's not going to tell us anything because of the inductive reactance. So we're going to actually have to calculate the amps. So we're going to come over here. We'll go to the primary side and we'll add a lead here. It's already set for 24 volts. Come over here, we'll set on 2 amps and we'll turn the power on. And we'll see that at this point we're pulling 70 milliamps or 0.07 amps. Same thing applies if we want to calculate that. We want to calculate the XL. We just use reverse Ohm's law. So we have 24 volts divided by our current of 0.07 amps. Which gives us an XL of 342.85, which is different than our solenoid. And so now we need to determine how many henries that transformer is. Now, most manufacturers are going to do this for you and simply print on the side of the component how many amps it draws. So here we have XL of 342 and 85.85 ohms. Let's go to our other formula here and calculate the henries. And rearranging this, L equals XL divided by 2 pi times the frequency of 60 hertz. Rearranging that gives us, I'm going to go ahead and multiply out 2 times pi, which is And the reason we use pi because this is a rotating magnetic field. Even though we look at it in a waveform, it's actually rotating up and down. So we use pi. .28 times 60 hertz gives me a value slightly different. It's going to be different than last time. Last time we calculated a XL 3.18 henries, but we calculated ohms. XL in ohms is 1200. Ours is going to be 342. 342.85 XL in ohms. We're going to divide by the result of that, which was 376. That value hasn't changed from the last one. Which gives us approximately a 0.90. You could round that up to 0.91 henries. So L equals 0.91 henries at 60 hertz for the transformer. Now, when you do skill 2, you'll need to have those values handy in order to do some of the calculations because they're going to be hooking them in series and parallel. But that is just to show you that there is a different value concerning AC and DC. Up to this point, we really haven't talked about that.